These are the earthquake notes, and we talk a little bit about mountains as well. Most of this just starts out with pictures of different earthquake damage from around the world over the years. This earthquake happened in Colombia in 1999. You can see how that bank just sort of shimmied its way down onto the road. And then another one in 1999 in Turkey. The building just completely collapsed. And then you can see this is a family member of that woman. And then with this earthquake that happened in Turkey, you can see the damage and the death toll that just radiated out from the epicenter of where the earthquake started, right there in the middle of the picture. 3 important questions that you should be able to answer by the time we get through with this. What is an earthquake? How do earthquakes occur? And where are earthquakes found? What is an earthquake? An area where there is a shaking of the Earth's crust caused by a release of tremendous amounts of energy. And right along this transform fault along the western coast of California is where there are a lot of earthquakes because of these plates moving past each other. And the elastic rebound theory is the theory that earthquakes occur when stress builds up between 2 lithospheric plates, overcoming the force of friction. This causes the plates to suddenly move and release energy and eventually snap back into their former shape, just like a rubber band. When you snap a rubber band, it goes back right to the original shape as long as you don't break it. And the different types of stress that's involved with this. Both isostatic adjustments and plate movement cause stress in rocks that make up the crust. Stress equals the force that applies pressure to the rocks in the crust. And there are 3 different types of stresses. Compression, you're pressing it. Tension, that's like a rubber band when you pull it apart. And shearing, like a pair of scissors. One's moving one way, the other piece is moving another way. So you need to draw these pictures there on your notes. Compression means when you squeeze the crustal rock together. You think about, you have a piece of Play-Doh in between your hands, and you press your hands together. You're going to squash the piece of Play-Doh. And then tension occurs when rocks are pulled apart like a rubber band. And then shearing, when rocks are being pushed in 2 opposite directions, just like a pair of scissors. One piece moves one way, the other piece moves the other way in order to cut something. What happens because of the stress? You have folding and faulting. When a rock responds to stress by becoming permanently deformed without breaking, the result is folding. This is how we make mountains. A syncline, sediments bend or fold downward. An anticline, sediments bend or fold upward. And these are the result of compression or pushing together. And on the picture, I actually want to show you a syncline. Syncline like a smile. You've got a little happy face going on here. And then an anticline is the opposite of a smile, so it's a frowny face, a sad face. If you look at that pink layer, it makes a frowny face, whereas the syncline makes a smiley face. And then faulting. Because of cooler temperatures and lower pressure near Earth's surface, rocks respond to stress by breaking or cracking. When there's no movement in the rocks along a break, it is called a fracture. When rocks do move at a break, it's called a fault. And the different types of faults, you have a normal fault, where the 2 pieces are moving away from each other, and this one's going to drop down. A reverse fault is when they're both pressing on each other, and this block on the right moves up. And then at a strike slip fault, One block's moving one way, one block's moving the other way, so this is horizontal, moving side to side. And then some more earthquake terminology. The focus is the area where the slippage first occurs. That's where the earthquake first starts. At the epicenter is the point on Earth directly above the focus. If you think about your skin is called your epidermis because it's on the outside of your body. Epi is on the outside. So the epicenter is above the focus on the surface of the Earth. And then seismic waves are the energy released in the form of wave motions in all directions from the focus. And there are 3 different types of waves. And then here's a little picture, should be on your notes. Got the focus down here in the middle, and then if you follow this dotted line up to the surface, you have the epicenter on the surface. And then there's that fault because of the break in the crust. You might need to write that on your picture if you can't see it. The P waves. P stands for primary. Primary means first. They travel the fastest and are the first to be recorded by a seismograph. They travel through all 3 states of matter, liquid, solids, and gases. The S waves, S stands for secondary. They're the second fastest and travel only through solids. So you might want to make a note on your paper. S for secondary, and S waves only go through solids. All of the S's go together. And then L waves. L waves, L stands for love. He was the name of the scientist that named the surface waves. They're the slowest waves, and they travel over the Earth's surface like ocean waves. They go up and down, and they're the most destructive because buildings just aren't created to withstand that sort of movement. And so here are the pictures. We've got a fence where there's no waves. S waves are kind of like a snake or a jump rope. If you have a jump rope, you're holding one end, somebody else is holding the other end, and they move in this S pattern. The P waves, they're like a slinky. They go in and they come out, and they go in and they come out, and in and out. Whereas the L waves go up and down like the ocean waves. When you want to locate an earthquake, to help locate the earthquake, we use an instrument that detects and records earthquake waves. It's called a seismograph. So the machine itself is the seismograph. By using the seismograph, scientists can figure out when the first P and S waves from an earthquake arrive at a seismograph location. And then here's a picture. You've got this whole seismograph. That's the whole thing. This little needle here has ink in it, and then when this whole thing starts to shake with an earthquake, it'll register on this sheet of paper. So that's the seismogram. Since the P waves travel faster than the S waves, the P waves made by the earthquake arrive first. The farther the seismograph station is from the earthquake, the larger the difference is in the arrival times for the P and S waves. So again, the farther away the station is, you get this bigger gap between when the P and the S waves arrive at the station because those P waves move so much faster than the S waves. And here's what's called a time travel graph. You need to write that on your notes because it's not written there. By determining the difference between P and S waves, you can locate the epicenter's location. And so we have the S waves here, the P wave there, the S wave there, and then when you look at the epicenter distance, how far away the earthquake was from the seismograph station, and you look at how long between, that's how you can figure out how far away. And in order to locate the epicenter of an earthquake, you have to take readings from 3 different seismograph stations. And then from each one, you get a circle. If whoever's in St. Louis says, oh my goodness, I felt an earthquake, and they call up these people in Berkeley and they say, oh yeah, we felt the earthquake too, and they each draw a circle away from themselves, well, they have to get on the phone and talk to somebody in Seattle and figure out, well, how far away was the earthquake from you in order to get a specific location. And that's what this shows here. You just make an arc with a compass, and then there's another arc with another compass, another arc with another compass, and then they all meet in one location. So that area in Montana must be the epicenter of this earthquake. Major earthquake zones. What's special about that picture down there? What's this area here called? Hopefully you're saying the Ring of Fire. There are 3 major earthquake zones: the Ring of Fire, the Mid-Atlantic Ridge, and the Eurasian Melanesian Belt. The Ring of Fire includes the west coasts of North and South America and the east coast of Asia. It forms a ring around the Pacific Ocean. And then it's the Ring of Fire because of all of the subduction and the fault zones, which cause all of those volcanoes and earthquakes. And then again up here on that map, here's the Pacific Ocean, and then it outlines the edge of the Pacific Plate all the way around. And then here's another picture about what's going on. Basically, the Pacific Ocean, if we imagine this is here, and this is kind of like Canada over here, it's pressing up into it. And then we're getting all of these arcs with all of the volcanoes, and then as this plate pushes in, it creates earthquakes right in this area. The Mid-Atlantic Ridge. It's where earthquakes occur because oceanic crust is pulling away from the sides of the ridge at a divergent boundary. It's kind of like if you rip a Band-Aid off of a scab and it starts to bleed again. That's basically what's going on here. So you've got 2 plates pulling apart and it leaves a big hole, and then from down in this big hole, magma pops up and solidifies and makes new crust. And then the Eurasian Melanesian Belt is where the collision of the Eurasian plate with the African and Indian plate. That's a continental collision. So if continental plates are colliding, we're actually going to make mountains. And that is exactly where Mount Everest is. And that's a picture of it right there. Wave velocity. By using a seismogram, that's the printout here from the seismograph, scientists have been able to learn more about the layers of the Earth. Since P waves slow greatly at 2,900 kilometers and speed up again at 5,000 kilometers, and S waves stop at the 2,900 mark, we can conclude that the outer core begins at 2,900 kilometers and is made of liquid material, because we know those S waves only go through solids. So if the S waves stop, it must stop being solid. And then if we look here, we've got the P waves that go, and then both waves hit something right here. And they must be hitting liquid because that S wave stopped right here. So everything's solid, or excuse me, everything's solid down through the mantle. And then once it hits the liquid, there's no more S waves. Also, due to an abrupt change in the P and S wave speed between the depths of 8 to 32 kilometers, scientists, this big long name, discovered the boundary between the crust and the mantle, and it's called the MOHO discontinuity. MOHO is obviously the abbreviation for his big long name right here. So, right at the bottom of the crust, in between the crust and the mantle, that's the MOHO. And then in this picture here, we've got an earthquake that happened here. It's emanating out those P and S waves, and then as they come through the Earth, they're going to go through the middle and come out the other side, except we've got this liquid core here. So there are no S waves that are going to go through there. And then when the P waves come through, it's almost like if you stick a pencil in a glass that has water in it that's halfway full, it'll look like a pencil's broken in half. That's that refraction from where it's in the water and then comes out into the air. And that's what happens with the P waves. They come through, and then when they come out of the liquid, they get refracted and bumped over to the side. So it makes what's called a shadow zone where there aren't any waves at all.